Hugh Everett was a graduate student of John Wheeler, who I think just recently died. Sorry if he didn't. He was a very, very famous physicist, and a lot of his students went on to win Nobel Prizes, so it's kind of a good thing. Everett came up with a hypothesis called the many worlds hypothesis, and he used this in his PhD thesis, but at the time Niels Bohr was alive, and Niels Bohr sort of is the head honcho, was the head honcho of the Copenhagen Institute, and they were kind of like writing the rules for how quantum mechanics would be promulgated through the profession. And his idea was, don't try to explain shit, just do the math. Don't come up with any interpretations. And unfortunately, Everett was forced to curtail his thesis so not as to offend Bohr, and Bohr was still slightly offended because he went against this dictate. And Bohr was such an imposing figure that Everett was not able to really get his work out there. And so he left physics and went out to be a businessman, and he was fantastically successful and apparently unhappy, and neglected his family and drunk himself to death and died at an early age. Now some people say that as far as science goes, if you can't test a hypothesis or a theory or a worldview, and the many worlds hypothesis is a worldview, that you really have no place coming up with it. It has to be testable. But of course there have been many examples of things that were not testable, that were developed over time, and then we developed the ability to test them. So I don't think that's a great argument. I think it's a good argument to say we just don't know, but I don't think it's a good argument to continue to explore these things, because by doing so you make it more probable that an avenue may arise as knowledge increases, so that it can become testable, falsifiable, etc. Anyway, what's interesting about the many-world hypothesis, and there are some different variations though, is that it potentially can reconcile Einstein's instinct, which was that the universe itself was deterministic, with the fact that we are essentially looking at a whole bunch of probabilistic events occurring in our universe. And probabilistic are things that have no cause. They're acausal. Many people have a hard time with this. Einstein did. And what the many-world hypothesis essentially is saying is that when an event, a quantum event occurs, and I suppose I can say that regular events, macroscopic events, can be looked at as an averaging of quantum events. But we're talking about when in an atom, let's say, a photon is absorbed, or an electron drops from a higher to lower energy state, releases a photon, all those kind of possible interactions, and there are many, all those would be quantum events. And then if you scale that up, you get the macroscopic events. And in scaling them, most macroscopic events appear to be deterministic. We believe that this is the case because the probabilistic events kind of average out, like flipping a coin. However, we do know that they don't always average out, and we can create situations that guarantee they don't average out. So how do you reconcile this with a deterministic universe? Well, if you think of the universe as a multiverse, many universes, and here's where it gets bizarre, because people say, well, you get lots and lots and lots and lots of universes in this multiverse, that seems like excess baggage. But here's the thing, the mathematics for quantum mechanics are the same whether you have a multiverse, many universes, or if you just have one. And it has a feature which is unique to all the other ways of explaining, kind of getting a worldview about quantum mechanics. It doesn't change the way you do the math, it doesn't change the predictions. But what it does do is it makes everything symmetrical. And here's how that works. You think of the multiverse as essentially existing as a potentiality, but it's completely deterministic. And everything that is going to happen will happen if you look at time as linear, which you don't have to do. But if you do, because that's a more familiar way of looking at things, then what happens is whenever quantum events occur, these little tiny events, there are different probabilities that may occur. And all probabilities that can occur do occur. And essentially, when they occur, they sprout new universes. But the whole thing is beautifully symmetrical. And it solves one of the real nasty, disgusting issues in quantum mechanics where, you put a cat in a box and some radioactive trigger either kills the cat or doesn't. You don't know if the cat is dead or alive. And inside the box, the cat is neither dead nor alive to you. And then you open the box and you find out the cat is either alive or dead, but there's someone else that doesn't know what you found. And for them, the cat is neither dead or alive yet either. And there's lots of other paradoxes like that, which I won't go into. But in the many-world way of looking at things, it's beautifully symmetric. Every time an event occurs, things split. Now, you're going to end up with just a multitude of universes, but there's something beautiful about it because essentially it's all deterministic when you look at the whole. But within a given universe, it's probabilistic. In other words, everything is probabilistic, even the deterministic stuff, but in the entire multiverse, it's entirely deterministic because everything that can happen does happen. Now, it's not the kind of causality we're used to, but there's a lovely symmetry to that, and I think that is like totally, totally cool. So, I could talk more about it, but that's kind of the idea. So, I love that idea. Now, it could be totally wrong, but I like the fact that you can reconcile Einstein's instinct and at the same time keep empirically what we're continuing to see is a probabilistic and not a deterministic universe that we live in. Yeah, so that's neat. The other thing I was thinking about is there's something called spooky action at a distance. That was something that Einstein really didn't like. And I'm just going to do a little trick here. It really doesn't, what am I going to use? Yeah, I'm going to use this yellow paper here, right here. It really doesn't address the issue in a very substantive way, but it's just a thought to give you an idea about how things work. Let's say that through a quantum event we create two photons. So these little beings here are the photons. And when they're created, they're essentially existing in the same space. And let's say they're going to be right over here. And then over time, the space between them is going to expand, like you see here. And what happens is, imagine they're up here, I don't have enough hands to do this, that we see the photons as moving apart this distance here, but in some sense, in some dimension, they're actually still in the same place, right over here. Now, that's a cool thing, because what happens is that when things are entangled, like these two photons, what happens is it's been demonstrated empirically, not just theoretically, that they exist as probabilities. They don't have actualities to some of the variables that define them. And this can be proven very easily mathematically. So it's not a question of hidden variables. There are things inside there we can't see, and that's why it's the way it is. No, they're just not there. And that's really been done very, very well a long time ago. Because all of quantum mechanics is a long time ago at this level that we're talking. But the bottom line is that when these move really far apart, and you take a measurement on this one, instantaneously, the other one is going to suddenly change in a specified way, a very precise way, instantaneously again across any distance in space. And so this idea of this unfolding space where the two are really in the same place, but space is expanding between them, is kind of like a baby notion of how to explain this. But you can do stuff like that by adding extra dimensions to the universe. And that's a cool thing that they're doing a lot. And some of the dimensions are curled up. They do that in string theory, where you have these big old planar dimensions and you've got these little curled up dimensions. And they're doing a lot of stuff with topology, which is, how do you explain topology? It's kind of the study of donut holes. It's taking Play-Doh and moving it around, but keeping the same number of holes and looking at the property. But they do that like in higher dimension spaces, and if you read Brian Greene's stuff, he explains all that. And he's got these weird-ass pictures, which are like three-dimensional of higher dimensional manifold surfaces and stuff. But that's just other cool stuff. Anyway, I'm going to like cut it off here because I can keep going, but I'm sure you just are saying, why haven't you talked about David? And I do want to say this about this. I mentioned in Jen's, I was mentioning why I like Stealth Badger's videos better than David's, better than Jen's. And the reason is he hardly ever mentions Variblast or David. Whereas Jen, she's constantly mentioning David, and I have absolutely no respect for people that are just living off, David. That constantly, that's all they have to do on YouTube is constantly making fucking videos about, a Variblast, David, super nigger, niggy nigs, crazy pants. I mean, they have no creativity. They're just leeching off him, and it disgusts me. It disgusts me terribly. There are people that don't even make videos. There's comments about it. All they do, their whole life on YouTube, like the new Love Helix or Danger Man 5. I mean, these people are foul. Thanks, folks.